All right, okay. At least I got the recording done. But so class, good morning. Welcome to CALC. I could not be there. I went to bed just fine last night and then was totally congested in the morning here. So I'm not sure what's going on here. So that's not good. Let's go with, see, and then my computer is acting up really, really bad. So let's talk real quickly here first. How did your, let's talk about Monday. How was Monday? Did you guys go and watch the video of that Mr. Suzuki?
Yes, we watched.
Yeah, we watched all 6.
Oh, no way. Okay, you guys made it through all of them. A good, bad, or ugly?
Repetitive. Boring.
Very repetitive. Yeah.
Sorry.
Saying the same thing over and over again. And it was like, okay, I got it the first time. I didn't need you to repeat that 5 times.
Oh, no way. It was supposed to, okay, sorry. It was supposed to build on each other, right? So you have the secant line, which is a average rate of change. Building on that, getting into the instantaneous rate of change. Building on that, getting into the formula that it's.
Yeah, that just kept going back before we go. Yeah, it did that. It's just like watching them one after another. Every time he would go back and explain the step before he did the next one. And since we were watching them consecutively, like, yeah, but it was fine. We got the average rate of change, everything. Formula, yeah.
Gotcha. Okay. Class, I don't know. Okay, let's see. I just want to make sure my mouse. There's the problem. My mouse being funny. Okay, so let's jam to this here. This is being recorded. Let me get out of here. Let me go to my screen. And as long as my mouse is going to be cooperating, we'll be okay. All right, so we got to the instant rate of change. We got to, let's see, the difference quotient formula. We got to that as well, is that right? Just talk to me what that means, or if you know what that means.
Oh yeah, no, it's the same. It's just the same as the derivative. Yeah, the f is it f prime a plus h minus f a and a divided by h? Is that what it is in terms of?
Correct. Yeah. And so and that was fun because that part that's the lecture that I really enjoy doing is when we get to one second. With calculus, because that's when we start up calculus here. Okay, my pin is ready. Everything's ready. My video's off. So now I think I can move my screen around. You guys tell me. You guys see a PowerPoint thingamajig in front of you? Is that what you guys see?
Yeah.
Okay, there, and should start working any minute here.
The screen is frozen.
Is my screen frozen?
Yeah.
Are you moving your mouse? I should turn that mouse. Kind of depressing though,
There it is. There's at least something there. All right.
Going somewhere.
It's a long time to swim. It is like not that hard to walk or run that. That's when it's a lot harder to for long distance.
Okay, you guys. So talk to me when. Talk to me if you if it's a repeat, right? Of what you saw. So we're at chapter 3. We finally started the derivatives.
You're really breaking up your voices. It's kind of hard to understand what you're saying.
Oh, okay. So let me bring it closer this way here.
That's better.
Okay. Derivatives, chapter 3. The cool stuff begins. I promised you the cool stuff will begin after Thanksgiving break, and then I was not even able to do a lecture of the cool stuff. So we'll continue. I'll give you guys the homework set tonight for chapter 3. So let me write down my notes here. Homework set, chapter 3. Cool. Anything else I need to give you guys?
No.
No, okay. So 3.1, yeah, let's talk here. Defining the derivative. This little fun little quotient. Seen that enough times already here, is that right? This is called the difference quotient. When you talk to me here, because I want to catch you guys up, and I want to kind of just get a feel of the videos and how much you absorbed from the videos. Are we good? You tell me if this is like, oh, let's do this here. Mr. Angie, it's a repeat, and we can just go on. We good?
Yes.
The difference quotient. Repeat. Did we get that already?
You wrote it slightly differently, but yeah.
Okay. So this whole concept of calculus is trying to figure out this right here. So if you have, let's go x squared, right? So if I'm here and let's say here, let's go 1, 1, right? I can always draw a slope line between those 2 points, correct? Slope, I already know that it's m is equal to y2 minus y1, x2 minus x1. Remember that one from a long time ago. And from the 1500s, we use that. We have been using it. The issue came in was the fact that I don't want it to be like that. If I'm going to calculate speed of something instantaneously here, I got to be able to move this little guy down so that it gives me a point at a single point. I want that to be the case. I want to be able to just sort of see that. So I want to be able to figure out the slope line at a single point, not 2 individual points. But my slope formula, you have to have it. And if you don't, then you're going to get a 0 in your denominator. Oh, we're good. Okay, you guys talk to me. Repeat or okay?
Okay.
Okay. Okay, let me give you this. Let me give you the lecture that I find fascinating with calculus. And then we'll set it up here. We want to go from here. We want to go from algebra. And eventually we want to set up calculus. And we'll get through to, in this time, I think we should get through that and start calculating formulas here. Let me just check one thing here. Oh yeah, this would be super cool. Okay, ready for super cool? Are we ready? So let's pick some points. Let's add some numbers here. This is x squared for us. The point that we're looking at is 1, 1. That's this point here. And so my job today is to figure out the exact slope at 1, 1. Did we do that from the videos? Did the guy do it from the videos?
Yeah.
What is the slope at 1, 1?
Yeah, remember it was like because we had the rate of change over 2 points, we want to find instantaneous change. And then it was like you want to find it as like with the a x equals a or whatever.
The limit
Yeah.
of the average rate of change.
The limit, yeah, the limit of
That
that.
life goes to 0.
Okay.
You want to find a 0 because we're not finding we want to find 1.
Okay, so he did it by numbers, right? So let's do this here. I'm gonna do it by just developing of the formula itself, and then using that formula in lines here. So let's do it that way. So if this was 1, 1, and we went from 2, 4, right, we can get the slope of that line. That's no problem. This would be 4 minus 1, 2 minus 1, and we get ourselves 3, 3. Are we good there? Does that make sense?
Yeah.
Okay, so let's do this by developing the formula. And this is over a progression of time. So I have this little slope formula.
Yeah, it's like the parentheses make smaller together.
And you guys talk to me here, see if this makes sense each time we do it, okay? Because it's kind of like the reiteration. So the question is this. Why can't I, if it's the slope formula and I'm using a function, instead of putting a y values in there, I'm going to use it as f of x values. Are we good there? And of course, I'll just be saying, are we good there all the time? So I'm not going to say that. Just tell me if you are stuck. So we went from here to here. So this is kind of like the evolution of the formulas for slope. And once we get it, then we're like, oh, I just need to do this to tweak it for calculus. So then the problem began in calculus to say, you know what? How about this? How about if I start at a specific point? So I want the 1, 1. My 1, 1 does not change for me whatsoever. It's this whole concept is I want to go a little bit beyond the 1, 1, and then I want to bring it back. And so in all this time in the developing of calculus, we're trying to figure out the little slope, instantaneous slope. So we're trying to figure out speed of an automobile right at that single value, right? Or speed of a something falling. And so the concentration was back then was to do this. We're going to take a single point. So x minus a. This would be f of x minus a, or f of a. And so that became a single point that you started off from. And what you did is you just had to calculate it. And so we, let's say we start off at x squared at 1, 1. And then we only went half out. Actually, let's do this just real quick on a calculator here. We're going to go from 1, 1, we're going to go half out and a tenth out. And so our formula would look something like this here, and we'll run out of room on this slide here. So let's say our f of x is equal to x squared. Our a value became 1, because that's where we're going to judge it from. And then the question is, what's the instantaneous rate of change at that point? Back to 1. So we did some iterations here. We said, okay, we're going to use f of 1.5, then we're going to use f of 1.1, then we're going to use f of 1.01, and we're going to see, after I plug it into this little function, I'm going to see what those numbers are getting close to, right? We're thinking limit in our minds, right? So let's do that just for this piece here, then we'll switch it up. Okay, are we good? You guys talk to me if that's something that doesn't make sense here. So here's my function. I'm trying to calculate this. And 3 hopefully will be enough numbers. And I'm going to go with a is equal to 1. I'm going to go with f of 1.5. So plug it into the formula. I'm going to go with f of 1, 1 minus 1.5, and this is f of 1.5. Okay, are we good there as far as numbers are concerned? And so let's start putting in numbers into here. So what is 1.1 squared?
2.21.
1.1 squared.
Or wait, this one,
Yo,
are you doing 1.5 right now for X?
yeah.
Yeah, you said, I don't know. Oh,
2.25.
Perfect. Thank you so much. -1 on the bottom. We get a what? A 1/2, right? Boom. So 1.25 divided by 0.5.
2.5.
I got 3. Is that 3? No, that's not 3. That's
2.5.
2.5. Thank you. Well, my eraser's not working. So 2.2. Okay, then we plug in a 1.1. Do the same thing here. So notice the top. Now 1.1 squared. 1.21 minus 1 over 0.1. Okay, calculate that for me, if possible.
2.01.
sure. No, 2.1 is if it's 1.01.
So that's what we're doing, right?
We're doing 1.1 first.
Oh, already. Oh, yeah. 2.1.
This one's 2.1, the next one's 2.01.
Because the f of x is x squared.
Yeah.
Oh, yeah.
You just squared that.
And then 1.01 is 2.01.
Oh.
Yeah, me too.
Well, it's not actually 2.
That's a good game.
Okay. But the calculator will be stupid around.
After we get to like 8, 5 or 6 difference.
What is that? Anybody? It was 1.01 squared. What is 1.0 squared?
I don't know what that is. No,
1.0201.
Thank you.
5 by 0.01 is 2.
Okay, are we good there?
Yeah.
Okay. So up until this point in the development of calculus, that's what we used to do. We used to just take a value called 1 or 5 or 12, wherever, whichever one we wanted to, and we would extrapolate more and more and more, and eventually we say to ourselves, you know what? I got it. When it reaches, this guy's going to 2, as the x's are getting closer to a, the value of, or the limit is actually going closer to 2. Are we good there? It's very much a manual process. So then the question is, can I make it even better? Is there any which way to make it even better? And this is where Leibniz comes in, creative genius with his notation. So let's go back to the notation that we had. Real quick, are we all done with this one? Sorry, real quick here. Kate, Taya in the back, are we good?
Yep.
So like at that point.
Okay, so then Leibniz comes on and he says, you know what? How about if we just change this formula just a bit? We're going to take this formula, and really what we're doing, let's get a position called x. So instead of a being the position here, I'm making x or x sub 1 or something like that. I'm going to make it so that we start off with an x. Here's my x. And then what I'm going to do is I'm going to add an h to it as I add more to it. And then the h is the piece that's going to go down to 0 for me. And so this formula then changed into this. It's going to be x here, f of x here, minus, obviously. But at this time, this is going to be f of x plus h. And this would be x plus h. Are we good there?
We did the video, basically, because we did the limit, we did the number, see how it got 4, 2 or whatever, and then,
Okay, are we good there?
Yep.
So then, if that was the case, this just reduces down to the top stays the same, but notice the bottom. What do we have on the bottom?
Just H.
Oh, just H, huh? Because the X's are gone. Okay, so then the question is, how does that help us? Well, what Leibniz decided to do is decided to, if notice the equations are all in terms of just X only. Notice the A value is gone. Notice there is no concrete X value you have to sort of be a part of, right? You're not tied to any A value anymore. So then Leibniz said, well, if that's the case, let me try this. Let me try F. Let me try the general function F of X. And here where things exploded. Because if we take this guy and we say to ourselves, okay, if F of X is equal to X squared, you guys talk to me. What is F of X plus H squared? Let's see. I think I remember my algebra days. This is X squared. This is X times H. This is another X plus H. And that's an H squared. So I think we got ourselves X squared plus 2XH's plus H squared. Are we good there? Okay, so I think we're good. Let's plug this guy in. Let's see what happens after we plug it in. So off to the side here, I'm going to plug into this formula for Leibniz. Let's see if Leibniz helps us out. So here's my general formula. I'm going to plug in my X squared formula, my original X squared over H. Good there so far? I noticed that the X squared here will cancel this X squared there.
and then we can get the 0 off the bottom.
And then we get ourselves da-da-da. And what Leibniz noticed as well is we got H's left. I can factor out an H out of this. H's are gone, and I'm left with 2X plus H. Okay, and that was a cool way to get H's out of there, first of all. Second of all, notice I'm not tied to I'm not tied to a single point. I'm not trying to figure out just the derivative right at, or the slope right at 2. This is a general function. And then the question becomes this. What am I trying to do with H here? Am I trying to make it bigger or trying to make it smaller?
Smaller, right? Because don't you want to get toward?
Absolutely. Trying to make it smaller because you're trying to get closer and closer back to that X that you had before, right?
You want the interval to be the smallest possible. You want it to be nothing. But
Yep. Eventually, Leibniz said, you know what? That's just what we studied before, isn't it? Isn't that just the limit? And what we're really trying to do is just limit as trying to get H to go to 0. And so this case, notice higher up right over here, I could not do that because H is on the bottom. We would be dividing by 0 and it doesn't work. Now that I've got H out of there, I go like this. Can I plug in a 0 for X? Sorry, can I plug in a 0 for H now? Absolutely. And then the question is, what in the world is 2x? What does that mean? What does 2x mean?
Isn't that the instantaneous rate of change at x? If you do limit as h goes to 0 of 2x.
Perfect. Almost there. I think we're sort of right around there. And notice it's not tied, right? It's just a 2x. Isn't that just the function itself as well? This is, okay, this is the coolness that it came out. So my original function is x squared. What I've just done is I figured out a formula that gives me, which is 2x. Sorry, 2x. That formula gives me the slope at every single piece according to the x itself. Let me draw it out a little bit better here. So let's take a look at some. So let's do this here. At 1, 1, right? We know that the slope was 2, right? Because we figured it out numerically, right? But this little function, we'll call it f prime. We'll just call it that right there. Slope of function. So I just figured a formula that gets me the slope at every single x from the previous function. So if I'm trying to figure out the slope right here, we did it manually before. So f prime of 1, that's where that 2 is right there. Didn't we get a slope of 2 last time? That's cool. Okay, how about this? F prime of 0, what would that be? That'd be 0. And as far as the graph is concerned, does that make sense that the slope is right here? Slope is actually 0. That's when it changes. The slope is flat. Okay, so the genius of Leibniz says this. If I know my function, and I can get this guy, as long as I know a function of anything, if I know a function of a rocket that's going out in space, right? And it's doing that right there. As long as I know its function, I can calculate its speed by this little process right here. Are we good? If I can create the function off of the object, like its placement, how fast it's going, the other way I can figure out the speed for any time, at any time of its rotation, right? So that's a rocket going out in space. I just have to plug in the value and I'm done. Are we good? I think that's super cool. Okay, we were not able to do it before. We could not do it with this because we were tied. One second. Right here. We couldn't do it here because we were just tied to specific value. So you could get, so you have to do the co-calculation all over again if you wanted another value that was not A. And so this little thing called the difference quotient now, or let's go with it here. So definition, derivative of a function denoted by f prime of x is, and it's this formula all over again. And so that tells us the speed of an object anytime. It tells you how fast something is going down. It tells you the curvature of something. So eventually. So awesomeness, because now at that point we were able now to calculate speed of objects, something that we could not do before. It opened up a whole new branch of mathematics, first of all, and and this was invented in about maybe like the 1500s, late 1500s. I'll say like this right here. And many people say it took about 300 years for it to sort of catch on. So by the time people were sort of like really confident in calculus, by the time you guys get the nice version, it was it was not a very nice beginning of it all first, and then also people had to be trained on it. People had to know what that is. So once, seems like it took a while for people to really grasp the meaning of calculus. And most people say all the inventions that are made, or at least a lot of the inventions made from the 1850s and on, is really just this development of calculus, harnessing the power of calculus. The fact that we can launch rockets into space. I mean, that's one thing. The fact that you have an odometer on your car. The fact that we judge movement of things, you know, that is all due because of this whole concept of I can finally calculate motion. I can finally calculate how fast something is changing. So are we good there? That's cool. I think that's like a super, super cool stuff. So exercise problem, let's go with it here. So can you find me the derivative? Let's try easy one first. Let's try easy one, then we'll move on to more difficult ones here. And then eventually, as things stack up on top of each other, eventually what we want to do is we want to develop quicker formulas to get to where we want. So this is just to sort of get us going. So can you find me the derivative of, oh, this one would be a good one to do. X squared minus 2x. All right, give you guys a minute here with this one. A little bit more challenging. We'll do a few challenging ones here. Eventually, what we want to do is we want to put into the difference quotient. And the only major bug in the difference quotient is this little f of x plus h. So instead of plugging it in, what we do is we just do it off to the side first, so then you don't have to mess with all the algebra that's behind it. And this should be very quick for you guys to do eventually. It's just x squared plus 2xh plus h squared. So then the distribution property. Okay, so that's the one that you want to plug in to the difference quotient. Okay, what I'm going to do is I'm going to let you guys try it yourself here. I'm going to make my camera a little bit bigger and wait for you guys just a bit here. Just for you guys to try it yourself here. All right, tell me when you're done. Tell me when you think you got it.
It was supposed to be plus 2h. So, because, well, it's f of x too, minus f of x, but f of x is x squared minus 2x. So if you're saying minus x squared minus 2x, then it's minus x squared plus 2x, right? I think they can be a type.
What?
I think you made a type. Because it should be x squared plus 2hx plus h squared minus 2x minus 2h plus x squared plus 2x.
That'd be 2x squared minus 4x plus, then you have to do.
Well, you can take out the x squareds because there are two of them. And you can take out the two x's, I think. Because there are two of them. And then you'll have.
2xh.
Wait, what's after plus 2h? What's after what, Kate?
It's minus 2x, minus 2h, what's after that?
Minus, so then you have to say minus f of x, which is x squared minus 2x. But if you're up in parentheses, the minus sign, it would be plus 2x, right? If you take out the yeah, so it would be plus.
Isn't what you wrote there
I don't think
x plus h minus fx, or is it just fx plus h?
minus f of x, because that's the formula. That's the formula, right? I think so.
All right, guys, any questions on it? Talk to me.
Did you make a typo on when you were writing out? Oh, wait, he was just writing out the. So on the for f of x plus h. Oh, you know what it is? It's 2h.
Yeah, sorry, that's right. I see it now. That's h. There should have been 2h here.
And then we just have to put in the minus f of x, and then.
Just in case x squared and 2x's.
Yeah, and the 2, yes.
Then it's just 2xh plus h squared minus 2h.
Yeah, and so then you can take out the h. 2x minus 2 plus h is 0, so that basically doesn't mean anything.
It's just 2x.
2x minus 2. Right.
Where are you getting the last x squared plus 2h?
So in the formula for the definition of the derivative, it has f of x plus h minus f of x. So you have to put f of x back in the.
Which is, I see it, that's right.
Yeah, but since it's minus x with minus 2x, it's minus x with plus 2x, which makes sense because we want to cancel out the x for 2x.
Okay, that makes a lot more sense. So,
Don't we?
Yeah.
I mean, I guess it doesn't really matter because it's not an h of one, but it would be nice.
so now
2xh plus h squared.
h squared.
2xh
No,
minus
it's
2 plus h. Wait, no, 2x minus 2x, minus 2h. Right? Because we have that 2h there that didn't get canceled out.
Yeah, 2xh and h squared are the only thing.
Isn't it 2x
Oh, yeah,
h plus
2h.
2 minus 2h? Yeah. So
Then
then
you
it
can
goes
factor out the h. Then it's just
2x minus
parentheses
2,
2x minus 2 plus 8.
which is 0. So,
Yeah.
All right, you guys talk to me. So let's see, Sadie, are we done? Are you done?
yeah, we. You that?
Yeah.
Yeah.
I got a 2x minus 2. Is that what I got? Is that what you guys got?
Yeah.
And here's the thing. When we find out, when you do something first time or when you contemplate something, you're like, yeah, that's so difficult. That's so difficult. And then when you finally accomplish it, like that makes so much sense and it's so simple.
I'm like, why did the Greeks think of this?
Right. Yeah, exactly. And so,
Their number, well, yeah, I don't know.
yeah, and they didn't think of I think it really took Descartes to kind of fuse geometry and algebra together, right? Because then you sort of saw the graphing of things.
Because everybody else thought of them as separate, sort of.
Uh-huh. And the other thing is there's always this sort of fascination in math history. Yeah, you can get actually a degree in math history and you teach math history, but the philosophical, how would you say, the question really is what could have been if the Greeks actually thought of calculus, right? How far we would be more advanced if they actually discovered it way back when, as opposed to all the changes that has happened so far. So I don't know. Things to contemplate here. Okay, let's jam. So that's this one. I feel a little more confident with it. And Sadie, you're correct. Like it's such an easy thing to think back. It's just when you initially think about it. Like summer, you guys didn't contemplate this during summertime. It just took now. Okay, my mouse is not going to the next slide here. So I'm going to go with this and I'll figure out. All right, another easy one or some tough ones. What do you guys say? What do you guys
Tough
say again?
one. Tough one.
Tough one. Okay, tough one it is. And your mark it set. Let's do the basic functions here. So there's my function right there, square root of x. Find me the derivative of the square root of x.
Okay, so that's kind of.
And so now the tough part is how do you get rid of that h on the bottom, right? Because that's where you get stuck. So give you guys a minute, contemplate it yourself, start the process, put it into the difference quotient. Let's see where we get stuck and see how we can get unstuck. And I'm going to try to unstuck my mouse here. Oh yeah, there it is. Okay, boom. Okay, finding the derivative of this guy.
We multiply by the conjugate of the numerator.
Then you have the.
But as long as it doesn't equal 0 or negative square root, it's okay. We don't care what the square root of the bottom, as long as it's not negative. Or 0. Oh, wait, right. No, because,
No, that doesn't work.
well, it might because,
Can we, why can't we, square the top and the bottom?
square them. No, because the problem with either of those ways, oh, no, we can't, okay, Kate, we can't square them because if we square them, then we'll have 2 times square root of x times square root of x plus h. But if we multiply by the conjugate, then we won't have any of those, we'll just have squared and we'll get rid of the at the square roots. Okay.
I think we're good. I think we got the little unstuck move. I think it is. It's the conjugate. So plug it into the value here. This is going to be.
So it's just
Oh, no, but,
h on top.
yeah, h on top. And
And
then,
just h. Then that cancels.
yeah, because there's
So it's
h
just-
times o.
1 over. Basically.
Well, it's not, oh, wait. Yeah, so it's square root of x minus, oh no, that's 0 too.
Yeah, then it's just 1 over root x plus h plus root x.
That's not real. It's root x plus h is root x. And it's minus. You don't know why.
What line? Talk. Is that what you guys tried?
That's
Wait, what
we
was
did.
the original?
Yeah, it's just root x plus h minus.
Oh, okay, never mind, that works because I switched the signs. Yeah. So it is plus in the top, so then it's 2 square root of x, 1 over 2 square root of x. Right?
Because the h is just a 0, so yeah, it's just 1 over 2 root x.
I mixed up the first problem and made it so the conjugate was negative, made it one negative conjugate. Not positive conjugate. Yeah. That would have made me square root of x minus 0. Yeah.
Okay. This is what I have. Yeah, I have the h on top, h is on the bottom, and I'm left with the conjugate still being on the bottom. Is that right?
You already learned it so many times, I always forget to do it.
I just leave it out to the end.
Yeah.
It's so annoying.
H is canceled, and I'm left with still the conjugate on the bottom. Conjugate is okay because I can plug in 0 in for h, and everything will be fine still. Well, okay, you talk to me. Is that the way you guys did it? Am I following you guys?
Yeah.
Okay. So I plug in the 0 in for the h's.
It makes sense, yeah.
And final answer, there it is. Shoosh. Okay, so go back to my algebra days. The square root of x is this little guy right here. Remember that as the function? So if that's the trajectory of a rocket or something else like that, here this will give us the speed at every single one point or the slope at every single piece right there. Okay, that's cool. That's a good one. Try next one. Next one, try. Let's see. Oh yeah, I have to do this one here. Sorry, go back here. Anybody not done yet? Needs more time. Go once, go twice. No, okay. Jam, here it is. F of x.
Are we sure we are? We had to do the review.
All yours for that. Have fun.
Okay,
So
okay, it's fine.
it had to get rid of the fraction over for
Oh, yeah, that's the, well. Let's see, we have x minus x,
okay, so
we
that
have
cancels out. So
h
it's
plus
just-
1 over x plus h plus
Wait.
1 over, minus 1 over x.
But isn't the h on the top and bottom also cancel out?
Huh?
So
Over
it'll
x.
just be
Wait.
1 over x plus h.
Wait. What?
Because on the top you have x plus h plus 1 over x plus h minus
Minus.
x over h. Right?
Minus x
Plus 1 over
minus
x.
1 over x. Minus 1 over x.
Wait, why is it minus 1 over x?
Because it's a negative, it's a minus. Wait,
So
so we
it
have, so
goes to both of them?
on the top you have x plus h plus
Plus.
1 over x plus h
Yeah.
minus x minus 1 over x,
Minus. Oh.
right? Because we have to put back in that f of x.
All over
I thought the f.
h.
Yeah, and the minus you can keep out.
Yeah, I forgot.
Yeah. And then we have an h, we can take out the x's.
Take out the x's and the h from the original.
How can we take out the h from the original?
Yeah, how can you do that?
No, it's,
How
Because
could
it's
you?
over, because they just divided.
So it's h plus 1 over x plus h minus 1 over x. We have to do some others
But
over
it's
multiple.
over h.
As well.
Isn't a fraction over
Yeah,
a
but
fraction?
but there's no h there.
No, but the h at the front of your thing cancels out one of them.
No, because it's adding, no, it's adding, and minus, it's not multiplication, you can't just cancel out, because we don't. Because we don't have an h in each return, it's on the top. I think what we should do, we should probably get common denominators on all the numerators, right? Or,
Go ahead. I'm just writing.
we had adding. I guess we could multiply, what we could do is make it all over x, all the things in the numerator over x plus h. So we have, h times x plus h plus 1 minus x, or wait, no. I guess we need to make it all over x squared plus h. Or no, wait, x squared plus hx. Let's see if that works. Times x each.
Wait, doesn't
No, because
a fraction over a fraction?
Because then when you have this over h, can you split it up into that? So it's like h over h plus 1 over x plus h over h.
You still have an h in the bottom there.
I know. I'm saying h over h equals 1.
Yeah, that part equals 1. So we have 1 here, and then we have plus 1
1
over
over
x plus h over h.
minus 1 over x.
Why would we want to do that? Because we still have a bunch of h's.
Yeah, we get there.
I think we should just make common, see if we can do it with common denominators and the numerators fractions. I'm not sure if that will work or not, but I think the common denominator would have to be x squared plus hx, which would be,
X squared plus hx.
yeah, because we have the x on the other one. That's the problem.
Then you have
X
to,
plus h. Let's see. So you have h times x squared plus hx plus x minus x plus h all over x squared plus hx. Is that right? I don't know if that's right or not. But then let's see if we can get, but we still have an x by itself. Oh wait, but no, we can do that because hx squared plus h, or, sorry, hx squared plus hx, plus x minus x, we get out the x plus h, there we got h. And then x, there's x squared plus hx on the bottom. Oh, but that's actually fine because it's hx now. Oh wait, all over h, we still have it all over h. And then if we can go, I guess we can,
That's cool. No, you guys keep on going. The only thing that, remember a long time ago when we were studying limits, we were able to split limits into 2 pieces or 3 pieces depending on additions.
yeah, that's what we should do.
Just to make it more simpler, I think I'm going to split this off like this. That becomes a 1. This is just 1 plus whatever I'm going to get out of here. Sadie, is that the direction you were going?
Well, I didn't think about splitting it, but yeah, now we can do what I was thinking.
So I'll let you guys work on that for a little bit longer here. So common denominators, absolutely. Get common denominators. Somehow, maybe that x will fall off. So I'll give you guys maybe like another 2 minutes here. 2 minutes for this one.
Okay, so 1 plus limit of the rest.
yeah, which is just 1 over x plus h plus 1 over x all over h.
So now we either need, okay, so I think we should still get common denominators of x squared plus hx. And we need h plus x on the 1 or we need x minus h plus x.
Isn't it h over x plus h over x? The way that the fraction's on top of the fraction.
What, Kate?
Everyone.
Wait, sorry, I didn't.
Wait, can we say we flip them?
Yeah.
Oh,
Like flip and multiply?
but it's not flipping. What it would be is it would be
H over
1
x plus h over
1
plus.
plus.
I know. Wouldn't they just get rid of the ones and then it would just be x plus h plus x over h? Or h over that?
Wouldn't it be 1 minus 1? Oh, but no, they're not common denominators still.
Oh, yeah.
We should make common denominators first. So we have, maybe do that when you're thinking after, okay? And so x, is it x minus parentheses x plus h?
Sorry, class. One more thing. There should be a minus sign right here, not a plus sign. Right here. I kind of, when that distributive property happens here, that 1 over x should have a minus sign in front of it. And common denominator is true. Let's go for the denominator. And I think we're like that.
X,
Over h.
okay, yeah, so it's h. Oh, there we go. Now, if you simplify that, it's x minus h plus x. Oh, wait, but it's minus, 2 minus.
No, look at what
Yeah.
he has up there. He just has x minus x plus h, which is
Yeah, right there.
X.
Yeah, no, well, x minus x is h. Yeah, h, and then x squared plus hx, and then it's over h, so that's fine. We can just say, divide the h's, then we have 1 over x plus hx.
Uh-huh. I think we're getting closer.
That's what I was trying to say, I just kept on messing it up.
No, you're doing good. Okay, so on top, the x's cancel, is that right? You got a negative h on top?
Yeah.
I think it's x and x plus h and then the h on the bottom.
Equals negative 1 over.
And then this changes into multiplied by reciprocal. So I'm going to do it on top over here because I'm running out of room. Limit as h goes to 0. I think we got what we need here. It's going to be negative h x plus h multiplied by the reciprocal h's are gone. I'm left with a negative there. That's true. And let's see what I have here. Limit as h goes to 0. Negative.
Oh wait, x times x.
It would be x squared plus x.
It's like, no, because it's x plus hx, and hx is 0, so
So
it's
just be-
x. Let's see.
Oh yeah, it has to be x squared.
Oh wait, there's an,
It would be x squared.
oh, because it's x squared, yeah, I dropped the x squared back, yes. X times x plus h.
Okay. You guys tell me, tell me when you are done.
You did it. Yeah, we're there.
All right, a little bit of a tough one there. All right, let's go back to what we discussed earlier in regards to, actually, let's go back. Yeah, let's look at a graph. So this is the computational way of doing it. Let's just take a look at a graph way of seeing it here. Or a little bit here. So let's see, I guess we could still call it a problem here. Exercise 2. And we can just say graph. Graph the derivative. And so let's go back over here to x squared. We know it's going to look like. X squared. All right, so notice on this one here, the derivative that we got was just 2x, right? So we want to see kind of just what happens here. Maybe we'll do the next one as well here. So whenever you have talking about slope, you're thinking about the slope process here. So on this side over here, is the slope negative or positive?
Negative.
Negative, yeah. And notice like about here, it's really negative, and about here, it's not as negative, right?
I think that's on his computer.
Is that on? No, it's on ours. It's on ours.
He's gone?
Yeah, he's gone.
Oh my God, I still see.
Still there. Don't do X. Just do the yellow one. Little.
He's still in the.
I guess they somehow just realized that we were both signed in on Mr. Andre's account,
There we go.
but not.
Okay, are we good here? Are we back?
Yes, I think so.
Awesome. Okay, thanks, guys. Thank you, Eli. Graphing the derivative. Let's take a look at a few things here. So on the left side, notice that little first red dot. That guy, the slope of it is pretty negative, right? It's a big negative number. The closer you get to 0, 0, the less negative you have. So the second dot is less negative. And notice at 0, 0, that's going to be, it's flat, correct? And so what you're trying to do is you're trying to draw the derivative, the value of the derivative. Oh, sorry, this is my, okay. The value of the derivative based upon if the negative slope is negative or positive or 0. So the best thing to do, let me just change to black right here real quick here, boom, is to figure out where does the slope is 0? The slope is 0 right here, and that's actually going to be a dot on the x-axis. If the slope is positive, we're going to be in the upper. We'll draw these because just to get used to it here. And if the slope is negative, obviously you're going to be down here. So you're corresponding the slope here to a dot over here. If this is less slope, therefore the dot is going to be a less negative number. The times where it's flat, it's always going to be a value along the x-axis. Then you're looking at a slope here that's positive, positive, and it's increasing positive, positive, positive. And so the value of it is actually going to go higher and higher. So let's try one. We're good? Let's call this A. A, let's try B. Okay, so here's my function. And then you guys got to draw for me the derivative here. It goes like this, here, 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 and back down. Okay, that's my function. Let's go with 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 hashtags there.
Wait, how are we supposed to know what?
We need the function. We need the function.
We know we're supposed to find the function.
Yeah.
But how do we look at
It goes up, it goes down, it goes down.
So let's go for it together. So notice, and let's think about slope first. So as you're coming down on this side right here, starting here, right, slope is negative, right? Negative, 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 negative. And then right at 2, you have a flat part, right? The slope. The object starts turning around, starts going higher, right? So the object is now going higher and higher up until we get to 7, and all of a sudden there's the other plateau that you have here, right? And then after that, it goes down and it keeps on going down. Okay, are we good there? Does that make sense as far as you're looking at the slope, but you're looking at it through the eyes of...
That points at 7?
Yeah.
If I'm going to graph the derivative, what I'm really interested in is the flat points, because the flat points give me a value of 0, which allows me to put a dot along the x-axis. Are we good there? There's that one. The other one is at 7. There's my flat points. There's the times where it... Okay, so now let's talk about it here. So notice that after this, the slope is positive for a little while, and the slope is increasing positive, and then all of a sudden, kind of almost like think of flat lines coming like this. So positive, shallow, and then it goes to a more steeper positive, then shallow, positive, shallow, positive. Good there? So the dots are, it's almost like, you can go like this even. It'll get us, you'll get used to it just a bit here. So right about here, notice right about here is where the slope stops increasing and starts decreasing, right? That would be your sort of the highest point along your dots for your derivative. Now, does it tell you how high it is, how low it is? Don't be interested in that. Don't, but just the fact that it's in the positive value, and that's where it changes the direction. Notice afterwards, this is all negative slope, negative slope, negative slope, negative slope, negative slope forever, right? So then the dots are negative, negative, and then this I'm going further and further negative. On this side, notice it starts off already a big negative and then starts curving down so that it flattens out. So this one looks like it's going to come like this. It's going to come from the bottom and then it comes like this. So the derivative equation, there's my derivative graph. Are we good?
Just do graph of the steep and slope.
Good job. So notice the interesting things are we grab the zeros. We've got to figure out what those are. And then we grab these little interchanges where the slope is changing from less steep to more steep and then just transitions back. Let's try one more. Let's try one more. Let's see if this will help. And I think we'll be done with that because we've got a minute and a half left here. See. Can you draw for me the derivative? Oh, move you guys here. It's going to go like this. Here's my formula. Oh, a little bit too fast here. And then back down. It's supposed to be symmetric. It's supposed to hit the 0, 0 marker right here. At -1, it's supposed to reach that max right there. At +1, it's supposed to reach the max, and it crosses at 2 and -2. So can you graph for me the derivative function?
Like twice.
Bless you, bless you.
The two dots under the big things.
Yeah.
All right, so you guys tell me, when is the slope, at what points are the slope 0?
2 and 1 and -1.
They're right there, right? It flattens out. It flattens out at 1 and also right at 0, doesn't it?
And 0, yeah.
Yeah, we got those 3 points there. Boom. And so notice it's all the way in the negative, but notice the slope here. Slope is hugely positive, isn't it? Positive, 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 positive. So my dots are coming like this. My dots are coming from the positive side. Then here, slope is negative, negative. Then the slope is positive, looks like positive here, and then negative afterwards here. So positive looks like goes negative like this. Then it goes positive. And then from here on out, then it's going to go negative. So here's my derivative graph. Very rough, but there's my derivative graph right there.
And it's not symmetrical, or it's not symmetrical like the other one because it was going from positive to negative.
True, yeah, correct. Okay, I think we're done for the day. Sadie or Katie, if I could have one of you guys wipe the chairs, as you normally do anyways here. All right, so we got through 3.2 for the most part here. I'm going to send homework for chapter 3 sometime today, and it should be good to go. Then we're going to see if we can develop formula rules themselves. Stuff to get us going. Okay. You guys on Monday of next week.
Hope you feel better. Yeah, feel better soon.
Thank you so much. I hope so too. All right, have a good weekend, guys. Bye. Oh, yeah. Let's see. Can someone also just tell Mrs. Rain to come in and turn off the equipment?
Yeah.
Yeah.
Thank you so much. I'm going to turn off my side.
I think it's kind of lame to have lived through a pandemic and not have gotten that.